Even blue.
I'll wait for yours.
Okay, our last talk before the break is Stephen Kyle, and he's our other current you teach student, and he has been working.
I'm going to get a job at Neville High School next year teaching chemistry and AP chemistry.
Okay.
Oh, yeah.
Say again?
Go ahead.
Okay. Very good introduction. Thank you, Dr. Cox. My name is Stephen. Most of you know me in this room. We've been working with Dr. Eklund this year. It's been a really great opportunity, and I'd like to tell you about what I've done this year. So we wanted to study the effects of the magnetic field on the Anodic Stripping Volammetry of lead using a cheap mechanical pencil electrode. So to give a quick rundown of electrochem in general, for those of us who may not understand completely, here we have a general metal, and we're going to supply it with an electron so that we have a redox reaction that takes place. But in the case of this slideshow, what I want to talk about is the half reaction that's going on here, not the full redox reaction. And I have a better one here. This is a glassy carbon electrode that I have a small cartoon of over here, and this is our reducing surface, what I will call the surface of deposition. And if I could convince you that we're taking, in my case, lead in solution, we're bringing it into solid phase onto the surface of deposition. So, in general, this is a 3-electrode cell. They come in many shapes and sizes, but this is just the most general version. Here, we're going to be talking mostly about the working electrode. As the diagram states, it's where the current flows and the potential is applied. That would be amps, volts. Those are more common words we use. But it does include a counter electrode and a reference electrode. So, to talk about our technique, the absolute basis for it is something called Anodic Stripping Volammetry. And what that means is, once again, a very simple rundown in steps there. We're going to use known solutions, known concentration solutions, to find out unknown concentration solutions. And how we do that is if I could convince you that the graph here, or the voltammogram rather, extends way out here, we apply a large negative voltage somewhere out here, and that causes deposition onto the surface of deposition. And then we start ramping it from a negative voltage to a more positive one, and these peaks include things like zinc, cadmium. These are not mine. These are very talented electrochemists. They are stepping up their concentration as they go along, and so that's why we get bigger peaks. But the important part is that this peak represents the oxidative part of the working electrode. It's the oxidative step where the contents are blasted off of the surface of deposition by oxidation back into the solution. So the inspiration and prior research for this year came from 2 major sources. One, we found that we can make some really cheap graphite electrodes with mechanical pencil parts. As I state here, though, we did find out eventually that we would like to make our own. This technique here was not very adequate for what we were trying to do, and I'll go into that a little bit later. The other major source of inspiration was that we found out that the deposition step of the technique is assisted by magnetic fields. And to give you just a little detail here, and you guys can see it over here, the surface of deposition starts to make these little islands of material, in my case lead, And the magnetic field assists by magnetohydrodynamic convection. It's a very fancy way of saying we have a Lorentz force involved, but we don't need to go too far into detail with that. What we wanted to prove was that, or support rather, is that we can combine these two to make a better technique. And of course, like I said earlier, we ended up making our own electrode that we think is much better. And we also wanted to bring this into educational opportunities. Most of you know, now all of you know, I'm an educator, so I'm always looking for opportunities to get things done in the college and high school classroom. So, how did we build our electrode? This is unique to us. We were inspired by the mechanical pencil housing, but we decided to go with another housing for the graphite. We take two glass tubes, and we had the idea to use a solder joint, and we connect those together. And so the solder joint provides two functions. One, the plastic parts on the outside make an excellent grip onto the glass, and the solder joint within melts, and you can see I've threaded graphite on one end and a copper wire on the other, and the solder joint binds those together for me. And so, excuse me, one more thing. We begin to glue the graphite in to seal it, and so we force a lot of glue down in there to keep it steady and things, but the most important part is that we want to eventually dry that glue and file it down the graphite surface so that we have a clean surface of glue and carbon, the graphite. And you can see it better here when I'm all finished. There's a surface of deposition. This is our working electrode, and that's our surface of deposition. But it takes polishing to get there as well, because we want a clean surface to deposit on. Now, this is proof of concept for our electrode. This is the electrode at work. I know it's kind of hard to see, but this leftmost electrode for you guys sitting over there, we can see that that's the surface of deposition, that's my reference electrode, and that wire is my counter electrode. And so I wanted to show you guys that this is a very representative peak, what I was seeing all the time with it. It was very robust. It would always give me these clean, uniform peaks, and that is a lead peak at around 1 ppm concentration. This is a 60-second technique, so I think that's pretty good. Unfortunately, when we tried to insert it into this rubber tubing, the glue fractured. So we were not able to use my electrode for the final setup, but like I say, this is proof of concept, it does work. And so we switched to a standard glassy carbon electrode, same concept. And the diagram here shows what's going on. If we can follow my pointer, the movement of water is around and around, coming from the beaker to the pump and back. We needed a mechanical pump, because if we use a usual stir bar situation, that's a magnetic field, and we're trying to isolate a magnetic field. And we supply it with this magnet here. Now, the big part, I need everybody to try to remember, this is just a device for myself. When I say 90 degree, I mean that the north pole of the magnet is facing the glassy carbon surface of deposition, all right? And when I say 180, I mean that the magnet has been turned away from the surface of deposition. I wanted to try both because of the drawing we saw, not drawing, but cartoon we saw earlier with the micro convection. And let's see, what else did we do? We pumped nitrogen through the beaker to get rid of oxygen, and we performed our experiments in these ways, like I said. We also used a aftermath software that controlled the potentiostat here, and the potentiostat is just a device that regulates how much potential is applied and how much current is moving through the working electrodes, and really all the electrodes rather. This is the data from the final setup. Here we have 1 ppm, 5 ppm, 10, 15, and 20, all lead. And these peaks show, they showed me promising results while I was doing it, but ultimately we need to look at the calibration data, but we'll get there in just a second. The most promising part of the data was here. I snipped this out for us. The 90, so 90 means North Pole facing the surface of deposition. 20 ppm, you can see the blue line up there. The 180 is the green. And we see that the yellow peak is the method used without a magnet at all. And so we can see a pretty good step up from that. And so the worst part about the experiment was certainly here at the 1 and 5 ppm samples. I do not have a good explanation why, but when we turn the magnet away from the surface of deposition, we can see that the peaks actually shrunk below where we think they should really be. But the calibration here on the two most important parts, we have the method without the magnet and the method with the magnet turned towards the surface of deposition. We can see that from here, the limit of detection was 0.36 ppm. These numbers are in ppm for the no magnet calibration, and the limit of detection on the 90 magnetic presence was 0.33. And the limit of quantitation similarly was 1.2 for no magnet and 1.1 for the presence of magnetic field. So, in conclusion, we can state that when we have our magnet, which was about 150 millitesla, whose north pole pointed towards the surface deposition, we had an 8.1% drop in limit of detection and limit of quantitation. And we can say that when the north pole of the magnet was turned away, there was a 6.6% drop in the limit of detection and quantitation. However, this is due to one, the field strength being decreased to about 90 millitesla when I turned the magnet, or the magnetic field orientation was best when the north pole faced the surface of deposition. And very likely it's a combination of both. My thanks first to Dr. Eckler, who's guided me through this research. My classmates, especially those who studied with me all throughout these years, have been extraordinarily helpful in this research. We've constantly bounced ideas off of each other, and really it does feel like a team effort, even though we're doing substantially different things. To the chem faculty and staff at large, you guys have helped me with my education a great deal, and to the College of Engineering and Science for giving us a platform to do this with. Thank you.
Okay, questions?